Down we go. 40, 50, 60. This is going to be a wild one. 75.
During the fifth decade at the NASA Dryden Flight Research Center, the F-18 High Angle of Attack Vehicle, or HARV, X-29A and X-31 explored the region of high angle of attack extensively.
Stick forward. 30,000. Stick neutral. Okay, I've got it. 27,700. Out to the right.
Historically, most combat aircraft easily lost control in this flight regime and frequently entered an undesirable spin. Angle of attack limiters were often implemented to prevent flight in potential spin regimes. The F-18 HARV was the number 6 pre-production F-18 aircraft and had been used previously by the Navy for spin testing. It was brought to Dryden in pieces on a flatbed trailer. It had been cannibalized and was missing over 400 parts. Dryden mechanics and technicians restored the F-18 and named it Silk Purse to indicate its transformation from a sow's ear carcass of missing parts. The F-18 HARV was flown in 3 configurations: the standard F-18 with thrust vectoring, and with thrust vectoring and actuated four-body strakes. Data was gathered on aerodynamics, controls, and propulsion.
Oh, that's great.
The HARV project produced some of Dryden's best surface and smoke flow visualization.
Nose coming down slow.
The flow visualization and surface pressure data was used to improve and validate computational fluid dynamics, CFD, and wind tunnel research. The thrust vectoring greatly improved the handling qualities at high angles of attack, and the HARV easily achieved its design point of 70-degree angle of attack in stabilized flight. Thrust vectoring also greatly enhanced the maneuverability of the HARV in mock aerial combat. The actuated nose strake concept proved to be a powerful and precise yaw control device at high angles of attack. The HARV program successfully developed new control design and handling qualities criteria for high angle of attack flight. The X-31 was the first international X-series aircraft with an international test team consisting of DARPA, the U.S. Navy, the German Ministry of Defense, Rockwell International, and Deutsche Aerospace. As the complexities of the program increased, Dryden and the Air Force joined the team, and the personnel and aircraft were moved to Dryden. The X-31 was designed for super maneuverability and used lightweight graphite epoxy thrust vectoring vanes instead of the heavy Inconel metal vanes of the HARV. The aircraft could perform controlled rolls at 70 degrees angle of attack and post-stall 180-degree turns at minimum radius, a maneuver known as the Herbst maneuver or J-turn. It performed many mock aerial battles with Dryden F-18s and Nellis F-15s and F-16s. As a final show of its capability, the X-31 demonstrated its exhilarating post-stall maneuvering at the Paris Air Show in 1996, creating quite a stir.
So cool. Holding and recovering. 700 feet, rolling into the slow speed. 3,000
In contrast to the F-18 HARV and X-31, The X-29A vehicle exhibited good high angle of attack characteristics without the need for thrust vectoring. At 45 degrees angle of attack, the vehicle demonstrated much better than predicted control and maneuverability. At high angle of attack, the flow on the wingtips of a forward swept wing remains attached and the ailerons remain effective. Conversely, for a conventional swept-back wing, the wingtip flow becomes separated before the rest of the wing and the ailerons quickly lose effectiveness. Even at 67 degrees, the maximum angle of attack achieved, the X-29A displayed limited control. The flight research into laminar flow control at Dryden culminated an experiment on the F-16XL No. 2. Active and passive laminar flow experiments had been tested previously on the F-104, F-111, F-14, F-18, Flight Test Fixture, Jetstar, and the F-16XL No. 1. For the proposed high-speed civil transport, laminar flow control offered the single most significant potential improvement in lift-over-drag ratio of all the aerodynamics technologies considered. A successful application could result in significant benefits in reduced takeoff gross weight, fuel burn, cruise drag, engine size, emissions, and sonic boom.
We're going to be on your left side taking some pictures of the glove, Dina.
On the F-16XL No. 2, a titanium glove perforated with millions of microscopic laser-drilled holes was attached to the left wing. Air was drawn through the tiny holes through ducting to a suction pump in the fuselage. This process results in a smooth laminar boundary layer on the surface and results in much lower friction drag than the normal turbulent boundary layer. Flight test results showed that laminar flow was successfully achieved to nearly the goal of 50% chord. In the support of the Space Shuttle program, a Convair CV-990 aircraft was modified to test Space Shuttle tires at various loads, side slip angles, and landing speeds. These tests were performed to expand the landing envelope of the shuttle. A specially designed landing gear was manufactured and installed between the main gear of the CV-990 and could simulate vertical loads of up to 150,000 pounds, side slip up to 15 degrees, and landing speeds up to 240 knots. A series of tests with the CV-990 were conducted at Edwards and at the Kennedy Space Center, Florida in 1993 and 1994. The tests demonstrated that the crosswind limits on the orbiters could be safely increased from 15 to 20 knots, expanding the orbiter's landing options. The Dryden tests also resulted in changes to the runway surface roughness at the Kennedy Space Center. During the mid to late 80s and early 90s, a series of integrated flight propulsion control research experiments were performed on a NASA F-15. The standard analog control augmentation system, CAS, was replaced with a digital electronic flight control system, but not replacing the standard mechanical flight control system. The engines were also specially equipped with digital electronic engine controls. Projects like the Highly Integrated Digital Electronic Control Project and Performance Seeking Controls Project demonstrated significant improvements in thrust, range, and engine life could be achieved by integration of digital flight, engine, and inlet control systems. The F-15 also successfully tested a self-repairing flight control system, where a control system failure could be detected, isolated, and the control system reconfigured to obtain satisfactory aircraft performance. This particular technology holds significant promise for survivability in a hostile environment. In July 1989, a McDonnell Douglas DC-10 airliner lost all means of conventional control when its tail-mounted engine exploded at 37,000 feet, severing the aircraft's hydraulic lines. The crew learned in real time how to control the aircraft by varying the thrust on the two remaining wing-mounted engines. With the emergency equipment waiting, the crew attempted to land at the Sioux City, Iowa airport. Although the flight ended in a fiery crash, nearly two-thirds of the passengers survived, due largely to the crew's heroic efforts. The accident inspired a Dryden engineer, Bill Burcham, to initiate a new project dubbed Propulsion Controlled Aircraft, PCA. Burcham envisioned software that integrated engine thrust with the digital flight computer to control the aircraft. During flight tests, engine thrust was commanded by the PCA software to respond to the pilot's control inputs, which he made using small thumb wheels on the mode control panel. In April 1993, NASA pilot Gordon Fullerton successfully landed an F-15 using only the engines with the PCA system. Following that success, in August 1995, the program reached its zenith. This time, Fullerton demonstrated the PCA system in a series of successful landings using only engine power for control on a McDonnell Douglas MD-11 airliner. While much of Dryden's research during this decade focused on high angle of attack programs, significant advancements were made on space shuttle tires and on the benefits of integrating digital flight and engine control systems.